Hey guys, welcome back to the channel and this new tutorial on Pytorch. So in previous quite a few videos we discussed various important components of transformer model, starting from like self-attention, then position embeddings, and then dropouts, and last video we covered layer norms. In this video, we will start implementing our transformer model. So first we will focus on this encoder part and we will implement that, and then we will implement the decoder part as well, and then finally we will implement and combine both with encoder decoder architecture with an example running. We will take like machine translation as an example and then train the model and see how it performs. Okay. Before going forward, we have a poll running on our YouTube channel. So I have added some topics what we want to start after the current transformer models tutorial. So go and vote your uh, options, and if you have any other topic, please let me know. I will add them as well. So we have at least like 3 weeks, like at least I will split the implementation in 4 tutorials so that it will be not too long. So let us dive in and start our implementation. So this is overall architecture of encoder decoder, which was proposed in attention all unit paper. So this image is taken from that. So we will focus on this part. So we have a multi-head attention which already implemented. We also learn about normalization, and this feed forward network is simply like we up project it and then down project again the output of the self attention uh, self attention module. Okay. And also we have these residual connections which we add from the output of the multi-head attention, and then we run the normalization. More concretely, we run layer normalization. Okay. So let us dive in and learn about like more detail with implementing it ourselves. To keep the implementation clean, what we did is we copied the self attention module, the final version multi-headed attention, in this separate code. So the only change I did is this head dimension. So generally what we have implemented, we accept the head dimension from the init function, but in general what is recommended is like we split the model dimension or the embedding dimension into n heads. Okay, that's what we did here. So the dimension of the model is nothing but the embedding dimension that would be input to the attention, and then as many heads we want to split it, we simply split it and then we get the head dimension. Okay, that is the one change. Other change I did is here in the unify head. So earlier the unify heads linear layer was with the dimension of heads into head dimension cross head dimension, whereas the correct output would be the dimensionality of the model. So if we are kind of dealing with typical use cases of self attention, so it should be dimensionality of the model. Okay, and the remaining code is same. There is no change as such. So this is the final implementation that we have done. The only change is this part where we are splitting the embedding dimension into n heads instead of using a separate head dimension. Okay, so let us dive in and start implementing. First what we will do is we will implement the transformer encoder layer, and then we will implement transformer encoder. So in transformer layer it will be just one layer, and in a transformer encoder we will simply make it like possible to create multiple layers. Okay, so let us dive in and create a class and call it transformer encoder layer. Okay, and as usual we will import NN module from Pytorch, and as we need to define init, we will define init, And what we need is, we need the dimensionality of the model, we need heads, and for feed forward we need FF size. Let us call it 2096, and also we need dropout, and let us define it 0.1. Okay, and also as needed we need to call super as well. And now what we need is, we need to define a self attention layer as we have in here. Okay, so first we will define multi-head attention, and let us call it self dot attention is equal to multi-head attention. Okay, and what it needs is, it needs dimensionally of the model and heads. Okay, next what we need is, we need a normalization for this, so we will call self dot attention norm, and it will be nothing but nn dot layer norm, which we have learned in the previous video, and the dimensionality would be d model. Okay, next we need to define self dot ff, which is feed forward network, and it will be a sequence of layers, so we will use nn dot sequential. Okay, and simply we will first start with nn dot linear, which will be like ff dimension, and then it will be, so first it is up projection, so it will be dimensionally of the model and ff size. Okay, and here we can see, then we need the activation function, and we will use activation function ReLU. Okay, and then we need to define a dropout layer on top of that, and then we pass the dropout value, and next we do is simply down projection, another linear layer, and that will be ff size cross dimensionally of the model. Okay, so this is our feed forward network as well there. Okay, and then we need another normalization function, and that, let us call it self dot final norm is equal to nn dot layer norm, and it will be similar to the dimensionality of the model, and also we need a dropout, so nn dot dropout and dropout. So that's our model implementation as such. So what we have is, this is our self attention or multi-headed attention, and then the corresponding layer norm, and then we have our feed forward layer, and then corresponding layer norm, and we have a dropout. Okay, so this is applied after each and every operation. So we will apply dropout after this operation as well as this operation. Okay, and now let us implement the forward method. So forward, what it will accept is, let us say it accepts x, and it also accepts x, let us call it source. Okay, embeddings, and let us call source mask. Okay, so in encoder we get source embeddings as input and source mask. Let us define it as a none, so that we can process only source embeddings. And next what we do is, we pass it through the self attention layer. So there is one more thing that we need to discuss a bit more detailed, which is called post-layer-normalization or pre-layer-normalization. So this is the original implementation or original idea that was implemented in a transformer model. So in this, you take input x and pass it through self attention layer, and then you aid it with the actual x and then apply layer norm. Okay, this is the uh, actual the original implementation that is there. But in literature there was a paper published which has shown like and even proven that if we apply layer norm beforehand, which they call is pre-layer norm, the training process is now more stable, or it trains more robustly and also quite faster. Because earlier when it was, I mean, if you see any original implementation and try to train it, it is very much sensitive to the hyperparameters. If you slightly change the learning rate, it won't converge. Okay, but if you change the post layer norm to pre-layer norm, it is now more robust. That's what they have proven. And if you want, you can try it out as well in your own implementation, but I won't go in that much detail. What we will do is we will implement the pre-layer norm transformer layer. Okay, so let us do that, because that's what is better, or that's what is shown to perform better and train better. Okay, so let us do that. So let us call tensor is equal to, okay, so first we need to apply layer norm. So what we will do is self dot attention layer norm, and then we pass source embeddings from here. Okay, and then we apply it to self dot attention. Okay, as we also have source mask, so we can pass it here as well. Even though it is none, it will be useful when we implement it with mask, and then we simply pass it through dropout. That's our first step. Now next step is to again do the same thing, like we apply first layer norm, and then we apply feed forward network and then apply dropout. Okay, so let's do that again. Tensor is equal to self dot final norm, and this will be tensor. Now we apply self dot feed forward network, and now again we apply dropout. And then we can simply return tensor. And that's our encoder layer. And that's our whole implementation of this particular module. Okay, now if we want to make it nx, which is like n times of it, we will simply create encoder module, separate one. Okay, where we will simply clone the same layer again and again, and then we will take it from there. Okay, so let us define that as well. So let us call it class Transformer Encoder, and similarly we will say nn dot module, and then we define init, which will take dimensionality of the model and number of heads and ff size. Let us make it fix, dropout. And definitely we need to call super, and that's our init. Now we can define a number of layers we want. Definitely we need to have it here. Okay, so let us call it num layers is equal to 2. Okay, and that's all the arguments I guess we need. And next we need is to define n layers. Okay, so what we will do is First we will say self dot layers is equal to nn dot module list. Okay, and that's where we will keep adding the layers. Okay, and then we can simply say for I in range num layers, let us call it num layers. Okay, and what we will do is simply we will create self dot layers dot append, and we will simply create transformer encoder layer. Okay, and what it accepts is dimensionality of the model and heads and ff size and dropout, and that's all. Now we also create a simple norm layer here as well, that will the final output will pass through that. Okay, so let us call it self dot norm is equal to nn dot layer norm, and it will be again dimensionally of the model. Now let us define our forward method, and similarly it will accept source embeddings and source mask. Let's make it none. Okay, now what we need is we need to just pass through the source embedding for each and every layer. So let us do that as well. So let us call hidden state. So just one more point to mention here, like we could have used here an endos sequential, but the thing is like in some cases we want the hidden states of the encoder and decoder to be at the output. Okay, that's why we need to use module list, so that we can process it one by one and get the all the hidden states at the output. Okay, so that's why we cannot use an endorsed sequential. We can use if we don't need that hidden states to be at the output of the encoder. Okay, so we will simply say for layer in self dot layers, and we will say tensor is equal to, let us call it source embedding itself. So what we'll do is we will get the output from encoder layer and then assign it again as a source embedding, so that the loop will continue. Okay, and we will simply say self dot, not self, we need this layer, and we pass the source embedding and source mask, and we can simply append it in the hidden state. So what will happen is that source embedding would be the output of the first layer, and then again it will apply the next layer and so on. Okay, so it is like cascaded hidden layers. And then at the end, when the loop finishes, we can simply return hidden states, all of them, and self dot norm hidden states minus 1. So the output is like the last embedding that we get as the source embedding. Okay, and that's all. That's like here we are saying we can create this transformer encoder, an instance of it, and that's our whole implementation for this particular box. Okay, so let us test it out. So let us create a main, and let us say dimensionality of the model we will want is 512, and let us create a source embedding dummy one dot rand. Let us say we have a batch size of 2, and let us say 32 sequence length and dimensionality of the model. So this would be the embedding, And then let us create an instance of encoder, and let us call it transformer encoder. What it needs, it needs d model is dimensionality of the model, num layers, let us call it 6, and number of heads, let us say we want 8 heads. Okay, and let us leave the other uh, parameters to the default. And now we will get the output if we pass through this embedding with this. Okay, so let us say we have h states and output is equal to model encoder and source embeddings. So now we can print length of h states. So it would be exactly same as number of layers, so it should be 6, and then we can print the output shape as well. So it should be 2 cross 32 cross 512. Okay, so let us run and see it if everything we implemented is correct. Okay, so there is this issue of dropout that we can easily fix. So here we have self dot do, not dp. Okay, so let us rerun and see it. So you see we have number of layers 6. So the hidden states are number of states we got are 6, and then the output is like 2 number of batch, and 32 is the sequence length, and 512 is the output. Okay, so I hope everything is clear, like how we implement it. It is quite straightforward, and yeah, so have a look at the code. I will share the link in the video description. So in the next video, we will start implementing the transformer decoder layer, which will be this part of the figure, only this part, and then we will later on in the third tutorial we will implement the whole architecture. Okay, and then probably in the fourth tutorial we will train the whole network, the whole model with machine translation task, and see that how it performs. Okay, so thanks for watching. Bye for now. Take care. See you in the next.